Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. In the previous video, we were dealing about valence bond theory. So moving ahead, in today's lecture, we will be studying about hybridization. So before studying hybridization, first let us take an example. For example, I am taking CH4, methane. Okay, and applying the concepts of VBT which we have learnt earlier, we will try to draw we will see how exactly the bonding is happening in case of CH4. Okay, so in case of VBT, what we have learnt, only the valence orbitals of the atoms participate in bonding, because the valence orbital is the outermost orbital and that only takes part in the bonding with other atoms, right? So the bonding or the valence orbitals of carbon and hydrogen, they intermix together, and for that intermixing, what was the necessary condition? Both these atoms must have unpaired electrons in its valence orbitals. So let's see, if I'm taking carbon first, or carbon is only the central atom, then its atomic number being 6. Its configuration comes out to be 1s2, 2s2, 2p2. Now, if I consider the valence orbital, which one will be the valence orbital? Obviously, this one. Here, the value of n is 2. So, the valence orbital will be 2s2 and 2p2. Now, if I try to draw this valence orbital, this penultimate orbital 1s2, it is not required, so we are not taking this into consideration. I am only drawing the valence orbitals here. 2s2 and 2p2. While filling this, each orbital needs to be filled up singly, then only pairing will start, right? Remember atomic structure. So here the configuration comes out to be 2s2, 2p2, and if you observe closely, we only have 2 unpaired electrons in carbon, right? So for bonding with 4 hydrogen here, it needs 4 unpaired electrons. Now from where will this carbon bring 4 unpaired electrons? See, this configuration is the lowest energy configuration, or you can say the ground state configuration. Ground state configuration. But when this carbon atom will see these 4 hydrogen atoms approaching from a distance, what will happen? This carbon will become, the carbon which was in ground state or the stable state now will become excited. Okay, now it will panic. Now these 4 hydrogen atoms are coming towards me. Where will I occupy these hydrogen atoms? I have only 2 unpaired electrons. Now how I will form bonds with these 4 hydrogen atoms? The carbon has the possibility that, okay, I have 2 unpaired electrons, I'll only take up 2 hydrogen atoms, let the other 2 hydrogen atoms go. But the carbon also has its own demands, right? The carbon also has to have 8 electrons in its outermost shell in order to complete its octet. So here, in order to bond with these 4 hydrogen atoms, the carbon has its own selfish motives. So what it will do? It will undergo, or it will move to an excited state, right? A higher energy state, which is the excited state. And what will happen in the excited state? Unpairing of these electrons. Okay, the paired electron which were present in 2s earlier will get unpaired, and the configuration will become 2s1, 2p3. 1 here, and all these are singly occupied. Now the carbon is having 4 unpaired electrons. It can easily form 4 bonds with 4 hydrogen atoms. Now the carbon and hydrogen bond here are of different types. How? See, this bond was formed by the overlapping of, okay, hydrogen's configuration was 1s1. So all the bonding that hydrogen will do will be from this orbital only, 1s1 orbital. So we have 2 different types of bond. One is SS bond and 3sp bond. Now we know the energies of s orbital is less than energy of p orbital. So here these 2 bonds formed are different in energy. Imagine a situation, you and your friend are going to a restaurant. Okay, So you had a plan of eating something special and you go to a restaurant. Now you have two different options. One restaurant which is serving your favorite food but at a higher price, and the other restaurant which is having the same food but at a comparatively lower price. So which one you will prefer? Obviously, where you have to spend less amount of money, the lower price one. So here, this hydrogen atom, four hydrogen atoms after coming from a distance, they will be observing we have two possibilities. One is a lower energy path, another one is a higher energy path. Now they will have a competition among themselves as to which one will go to a lower energy path. And every atom in the universe always wants to follow a low energy path, right? Even we also as humans, we want to follow, or we want to do the work which is less tiring or less requiring less amount of energy, right? So same is the case of atoms also. So there will be a competition between these four hydrogen atoms as to which one will bond with this orbital, s orbital, which is comparatively of a lower energy path. Now, for this, to avoid this confusion, what basically this carbon does is, okay, so how did we know that these are higher energy, lower energy? How did we come to this conclusion? See, after this bond was formed, we experimented out, and through experiments, we concluded that all these bonds are of equal energy. All the carbon hydrogen sigma bonds are of equal energy. So what might have been the possibility? Okay, so what must have been done? S orbital, which was at a lower energy state, and p orbital, which was at a higher energy state. What they did, they basically gained and lost some energy to come to a equal energy state, right? Basically here what basically happened is you and your friend were having 5 rupees, your friend was having 100 rupees, and what I did was mixed that 105 rupees of yours as well as your friends, and then that became 105. I distributed that 105 equally among you and your friend. Now there is no partiality, nobody is having less or more. The same thing happened with this carbon also. Carbon basically intermixed its s and p orbital and formed four different orbitals, but here equal energy, right? Here it was having 3 p orbitals and 1 s orbitals, right? So now what happened? They intermixed among themselves and they formed 4 new orbitals. But these new orbitals, what was the characteristic feature of these new orbitals? They had equally, or they had same energies, right? So basically this intermixing of orbital is called as hybridization. Okay, so what is hybridization? Intermixing of orbitals is called hybridization. Now, if imagine two friends, one was having 100, one was having 5, the other which was having suppose say 1000, and that was another one was having 1 rupees. Okay, so where the mixing would be compatible, where the other person bearing the higher amount of energy or the higher amount of money will not be hurt. Obviously where the 5 and 100 rupee case was there the difference was comparatively to the other case, the difference was minimum or less than the second case. Here one was having 1 rupee and the other was having other was having 1000 rupees. So intermixing in the later case was comparatively difficult than the first case. So same is the case with orbitals also. The only those orbitals intermix which are having same or nearly same energies. Orbitals having huge differences in energies, they cannot be intermixed. Okay, they will not be compatible with each other. So orbitals having same or nearly same amount of energy, only those orbitals can be intermixed among themselves, right? So now let us after understanding or after having a basic idea about hybridization, let us see some important points here. So first is atomic orbitals of same or nearly same energy intermix to give new orbitals of exactly same energy, right? And what all orbitals can intermix among themselves? All. Whether it is half filled, whether it is fully filled, whether it is empty orbital, anyone, all the 3 orbitals or the 3 possibilities, they can intermix among themselves. They do not distinguish or they do not have any partiality between orbitals. So half filled, empty and fulfill orbitals can take part in hybridization. Next is number of hybridized orbital is equal to number of hybridizing orbital. For example, in the previous case, that is CH4 case, I took one s orbital of carbon and intermixed it with 3 p orbitals. So now I will get how many sets of hybridized orbital? 1s and 3p. So total 4 set of hybridized orbitals, right? So number of hybridizing orbital or number of hybridized orbital is equal to number of hybridizing orbitals. Okay. So number of hybridized orbital is equal to number of hybridizing orbitals. Next is to find out hybridization, we only consider sigma bonds as well as lone pairs. Pi bonds have nothing to do with hybridization. Remember this one. Pi bonds are not included in hybridization in any case. Pi bonds are not included in hybridization. Okay. So pi bonds and sigma bonds and lone pairs are considered only. Okay. Hybridized orbitals are named after the parent atom. Parent atom means the hybridizing orbitals. For example, if I'm taking 1s and 3p, I'm getting 4 hybridized orbital. So the name of this hybridized orbital will be sp3, right? If I consider a case where I'm taking 1s and 1p, the hybridized orbital I will get is 2 sp orbitals, right? This was having 1s and 1p. Now if I will hybridize them, I will get 2 number of sp orbitals. Clear? If I'm taking 1s and 2p, I'm getting sp2 hybridization. If I'm taking 1s and 3p, I'm getting sp3 sp3 hybridization. If I'm taking 1s plus 3p plus 1d, I'm getting sp3d hybridization. If I'm taking 1s plus 3p plus 2d, I'm getting sp3d2 hybridization. Correct? Okay. So here how many number of hybridizing orbitals? 2 plus 3, 5 plus 1, 6. Got it? Now if I'm taking 1s plus 3p plus 3d, what I'm getting? sp3d3. Okay, all the hybridizing orbitals are named after their combining parent orbitals, right? Now hybridized orbitals are named after the parent atom. Now the shape of hybridized orbital, right? So if I'm taking 1s and the shape of p is this and d was double dumbbell, but the shape of all the hybridized orbital is like this. We are having one bigger lobe and one smaller lobe. Okay, this is the primary lobe. This is the secondary lobe. This is the bigger lobe and this is the smaller lobe. And while drawing the structures, we usually omit this smaller lobe. We only take into consideration this bigger lobe. Now what happens? These hybridized orbitals, what they do, in order to minimize repulsion among them, they are basically electrons only. So in order to minimize repulsion among themselves, they spread out in space so that repulsion can be minimized. And that spreading out of hybridized orbitals in space lead us to the concept of geometry. So basically we can conclude that hybridization gives us information about the geometry of the molecules or the structure of the molecules, right? VBT was not able to give us any information about the structure of molecules. It only gave us information about how the bonding exactly happened, right? But from hybridization, we can draw sufficient information about the geometry of the molecule. How? We will deal in this video only in the later part. Okay. Now, after learning all these about hybridization, your question might be coming, how to find out hybridization for any given atom? So in this video, I will give you a shortcut trick where you can easily or quickly find out the hybridization of any molecule given to you, molecule or ion even given to you. So first of all, we need to find out the value of Z. Okay, Z is number of hybridized orbitals, right? So in order to find the value of Z, you have a formula. Z equals to half of, and remember, hybridization is only and only found out for the central atom. Okay, central atom, if you're considering only a single atom at a time, basically. Okay, so here valence shell or valence electrons of the central atom plus any negative charge minus any positive charge plus number of monovalent got it, valence shell or half of valence electron of the central atom and plus any negative charge minus any positive charge number of plus number of monovalent atom. Okay, how will you find the value of Z? For example, let me take NH3. Okay, in NH3, I will ask you, find out the hybridization of this nitrogen atom. Okay, how will you find? Formula, half of number of valence electron. Okay, what is the valence electron of nitrogen? The atomic number for nitrogen is 7. So configuration will be 2, 5. So hybridization is 5. Number of valence electron is excuse me, number of valence electron is 5. Plus, is there any negative charge? No. Is there any positive charge? Obviously no. But number of monovalent atoms we have here is hydrogen bonds forms one bond, right? So the number of hydrogen atom is here is 3. So number of monovalent atom is 5 plus 3, 8 by 2, it is 4. Okay. So this is the value of Z. Now if I say water, H2O, and here I will say find out the hybridization of oxygen. How will you find? Same, half of valence electron. How many valence electrons? Oxygen atom is having atomic number as 8. So configuration will be 2, 6. Number of valence electron is 6. Plus any positive charge? No. Any negative charge? No. Number of monovalent atom here is 2. Because 2 hydrogen atoms. Again 6 plus 2, 8 by 2, it is 4. I think now you might have learned how to find the value of Z from this formula. So using this formula, you can find out the value of Z of any given atom or ion, okay, any given molecule or ion, right? Now, after finding out the value of Z, what will you do? If the value of Z is, suppose here Z, and here I am taking hybridization, and in the same trail only I am giving you idea about geometry, right? Geometry is basically arrangement of electrons. Okay, so if I get my Z value as 2, minimum I can get is 2 using that formula. So its hybridization will be S, P, and geometry will be linear. Okay, how? If A is the central atom, it will be bonding with 2 other atoms, B, B. Got it? If Z value is 3, the hybridization will be S, P, 2, and the geometry will be, if this is the central atom A, 3 other atoms are bonded to it, B, B, B. This is trigonal planar. If the value of Z is 4, hybridization comes out to be sp3. The shape or the geometry will be tetrahedral. Tetrahedral. So four other atoms will be arranged in a regular tetrahedral manner. If the value of hybridization comes out to be 5, the hybridization will be sp3d. The shape will be C. If the central atom is A here, 5 other atoms will be placed. 3 will be placed in the plane. These B, B, B. These 3 atoms are placed in the plane. This one, and this one. These are in the plane. And one is above the plane and the one is below the plane. And here the geometry comes out to be trigonal bipyramidal. Trigonal bipyramidal. If the hybridization comes out to be 6, if the value of Z comes out to be 6, the hybridization will be sp3d2 and the geometry will be octahedral. These are the values, these are the shapes or geometries of the molecule, and children, you have to remember this in order to understand the structures or the further theories of this chapter. Okay, so how will be present? I'm drawing it here. A, B, 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 one above the plane, one below the plane. Okay, here I'm adjusting. If the value of the Z will be 7, the hybridization will be sp3d3 and the shape will be pentagonal bipyramidal. And how will it look? A, this forms a pentagon, one above the plane, one below the plane. You will connect all the surface, you will get a pentagonal bipyramidal geometry. Okay, so this is it for hybridization. Considering these hybridization and geometry and the formula I have given, you can find out the hybridization of all the molecules or the ions which is given to you. So like after this video, you can come across or you can practice some of the questions from your book. That's all for this. In the next lecture, we'll be dealing with VSEPR theory. Thank you.